everybody, hope you had a nice spring break. It's actually still spring break, it's Saturday, but I'm trying to get a head start on some of these videos for this week. Today we are going to be working on part 3 of sections 8.1 and 8.2. So if you remember before spring break, I know it's been a while, we were graphing exponential functions. We saw growth functions. Remember, it was a growth function if our base was bigger than 1. It was a decay function if our base was in between 0 and 1. We also learned how to use the compound interest formula, and there were a lot of variables there. So keep all those things in mind because we're going to be having a quiz next week that's going to cover 8.1, 8.2, and 8.3. But today we're going to focus on part 3, and we're going to be working on word problems. And I know that sometimes word problems are a little intimidating for students, but I think you'll get the hang of these pretty quickly and easily. We're going to start with talking about exponential growth equations. Remember, we already said before spring break that a growth function is when your base is bigger than 1. So that means that it would be no surprise here that we have 1 plus r because we're going to create a base that's bigger than 1. So let's talk about what these variables mean. A represents your initial amount. So it might be money that you are putting into something. Maybe you're buying something. Maybe you're depositing it into a bank. Whatever you're starting with, that's your initial amount. R is going to represent your percent increase, but notice that it says it's written as a decimal. So typically what's going to happen is you're going to be given R as a rate, as a percent, and you have to remember to change it to a decimal. So that's going to be something you remember to do. 1 plus R, which again is that part that I underlined, we call that the growth factor. So whatever 1 plus R is, that's your growth factor. We still have the variable T. T is going to represent your time. So let's just jump right into example number 1. It says in 1995, there were 275 cell phone subscribers in Aiken. The number of subscribers increased by 75% per year after 1995. Write an exponential equation that models the number of cell phone subscribers after T years. How many were there in 2004? So for this particular problem, there are going to be 2 answers. One answer is going to be to write the exponential equation. The second answer is we're going to use that exponential equation to answer how many there were in 2004. So we need to identify the A, the R, and the T. So let's start with A. Remember, A is your initial amount. Well, in this particular problem, it says initially in 1995, there are 275 cell phone subscribers. So that right there is our value for A. That's the initial amount. It says the number of subscribers increased by 75% per year. That's going to help us come up with the R, but remember for R, we have to turn it into a decimal. So right now we have 75%. Just as a refresher, to change a percent into a decimal, we're going to take the decimal point, which even though we don't see it, we know that it is directly behind the last digit. We're going to move it 2 places to the left. So our value for R is 0.75. So for the first part of this answer, it says write an exponential equation that models the number of cell phone subscribers after T years. That means right now we're not going to plug anything in for T. We're going to just use T as a variable. So I'm going to have Y equals, now I'm going to plug in my value for A, which is the 275 cell phone subscribers. Parentheses 1 plus R, we already determined that R is 0.75 raised to the T power. And I'm going to go ahead and just simplify that real quick. And by simplifying, I mean going ahead and adding what is in the parentheses. So 1 plus 0.75 turns into 1.75 raised to the T power. That's going to be the answer to the first part of the problem. We have written an exponential equation. Now the second part says how many were there in 2004? So this is where we got to go back and say, okay, 1995 is when this problem has started. that's going to represent year 0. T being 0. That's the original date. That's the initial part of the problem. That's when the problem begins. So T equals 0. How many years later is the year 2004? Well, it's 9 years after 1995. And so that means that T is going to be equal to 9. So I'm going to take that equation that we wrote. So I have 275 in parentheses 1.75. And now I'm going to plug in a 9 for the T. And then here's where I need a calculator. So I have 275 parentheses, I don't know if y'all can see that, 1.75 close parentheses, and I'm going to raise it to the 9th power. All right, now remember that what is this number representing? We're trying to find out how many cell phone subscribers there are. That means people, and we don't want part of a person, do we? We want whole numbers. So I'm going to approximate this. I'm going to use the approximate symbol. I'm not going to use an equal sign because I'm rounding it. I'm going to round it to the nearest whole number. So after those 9 years are up, we have approximately 42,333 cell phone subscribers. I'm going to keep my units there, subscribers. So we have 2 answers to that. The first answer was the equation, and then we used the equation to find out how many subscribers there were in 2004. All right, example number 2 says in the exponential equation y equals 35 times 1.27 raised to the x power, identify the initial amount, the growth factor, and the percent increase. So we're not actually going to be using a calculator for this one and solving anything. We're just going to identify amounts. So remember the initial amount, that's your value for A. Remember we saw that's what's in front of the parentheses. Well, for our problem, A is 35. So for the initial amount, it's 35. Then it asks us to represent the growth factor. Remember the growth factor is 1 plus R. That's what's in your parentheses. So for us, that's the 1.27. And the last thing that it asks us to identify is the percent increase. Remember, that's the R. Well, we've already identified that the 1 plus R is 1.27. That's what we just said in part B. So I'm going to solve for R, subtracting 1 on each side. Remember, line your decimal points up. There's not a decimal point with the 1, but we know that means that it's directly behind it. So I get R equals 0.27. Now this doesn't answer our question because notice that it says percent increase, and what we have is not a percent, it's a decimal. So I have to take my decimal point, move it over 2 places to the right, and I'm going to get 27%. That's how much the increase was. All right, example 3 says bacteria can multiply at an alarming rate when each bacteria splits into 2 new cells, thus doubling. If a scientist starts with 3 bacteria, which can double every hour, how many bacteria will she have by the end of the day? Okay, so let's go back and look at the problem. We want to look for things like what's the initial amount, what's the rate of growth. So it says bacteria can multiply at an alarming rate when each bacteria splits into 2 cells. So in other words, we're starting off with 1 cell and then it splits into 2. Well, what kind of growth is that? If you start off with 1 and you end up with 2, that is actually a 100% growth. All right, now what would that be as a decimal? Because remember, you have to change R into a decimal. Well, I need to move my decimal point 2 places to the left, so my value for R is 1. All right, it says if a scientist starts with 3 bacteria, the 3 is going to represent our initial amount. So we now know what A is, and they are doubling every hour. How many bacteria will she have by the end of the day? Okay, well, let's look and see what's happening because it's doubling every hour. and we want to know how many she's going to have by the end of the day. What do you know about hours in a day? There are 24 of them. So our T is 24. So here's our equation. Y equals 3 times 1 plus R. Remember the R is 1, and we're going to raise it to the 24th power. Here's what I want you to notice real quick, because I think that if you can notice this, this is going to make problems like this easier. Inside of the parentheses, when you add 1 plus 1, obviously you get a 2. Let's go back and look at the word up here that was so important, doubling. What does it mean to double something? That means you have twice as many as you had to begin with. Notice what this base is, a 2. So if you want, when you see that word double, you don't have to go through the process of trying to figure out the R and then putting it in. If you see that word double, that means your base is going to be 2. What if you were to see the word triple? Your base would be 3. What if they use the word quadruple? Your base would be 4. So if you can pay attention to those words, it will make these problems much easier. Now we just need a calculator. So again, we're going to do 3 times 2 raised to the 24th power. I don't know if y'all can see that. It's kind of sunny in here. Look at that number. It's pretty huge. So after only 24 hours, let's look at this number together. We have 50,331,648 bacteria. That's a lot of bacteria after only 1 day. All right, example 4. In 1970, the population of a city was about 278,000. So right away they're telling you your initial amount. Since then, the city population has grown at an average annual rate of 1.8%. All right, remember, that's obviously your R. But remember, you have to change it to a decimal. You might be wondering, well, there's already a decimal point there. And you're right. The problem is it's still a percent. So you need to change it to a decimal. So we're going to have to take this decimal point, move it over 2 places to the left. And what that means is we have to add in a 0. So we're going to have 0.018. So even though there's a decimal point already there, you still have to change your percent into a decimal. So part A says write an exponential equation that models the population of this city T years after 1970. In other words, don't plug in a number for T, continue to use the T. I'm going to write here off to the side because I think it's kind of hard to see it on this color. So I'm going to have Y equals 278,000 parentheses 1 plus R close parentheses raised to the T power. I would be okay if you left your answer like that. If you would like to go ahead and add those values together, and I'm going to do that real quick. So I have 278,000 parentheses 1.018 raised to the T power. That would be a great answer too. Letter B, about how many people lived in the city in 1990. Well, look at the problem. It starts in 1970. Remember I told you that the beginning of the problem represents the year 0. 1990, how many years away is 1990 after 1970? It's 20 years later. So we're going to be plugging in a 20 for the T. So we've got that 278,000. Sorry, this shakes so much, y'all. Parentheses 1.018, close parentheses, raised to the 20th power. So let's plug it in. 278,000 times 1.018 raised to the 20th power. I'm getting this number. Hopefully you can see it. What does this number mean? Well, remember this number means the number of people living in the city. I have a decimal. I don't want a part of a person, I want a whole person. So I'm going to round that and say that it's approximately 397,192 people. So I rounded it because I don't want part of a person. Letter C, what is the population of this city today? Well, today means the year 2020. Remember, 1970 was year 0. 2020 is 50 years after 1970. So this time we're going to be redoing this problem. And again, we're going to be plugging in a 50 in place of t. So let's see what this looks like. 278,000 times 1.018 raised to the 50th power. Again, I get a decimal. I don't want a decimal, I want to round it to the nearest whole person. So I've got 678,319. That's how many people would be in the population of that city. All right, so we've talked about exponential growth equations. Now we're going to shift gears and talk about exponential decay. But they're essentially the same type of problems. The biggest difference is instead of a 1 plus r, we're going to have a 1 minus r. Because remember we said that for decay problems, your base needs to be between 0 and 1. So it's going to be smaller than 1. That's why we're subtracting the rate instead of adding the rate. The a is still the same thing. It's the initial amount. T still represents your time. R still represents your percent, but this time we call it a percent decrease because we are going down instead of going up. And that means that 1 minus r is going to be called the decay factor. Remember, 1 plus r was the growth factor because we were adding. 1 minus r is going to be the decay factor. Everything else is identical. So example 5, Jolene purchases a new car for $22,499. The value of the car decreases by 11% each year. Write the exponential equation that models the car's value after t years and then find its value after 3 years. So again, we're going to have 2 answers. The first answer is an equation where we use t in our problem. The second answer is going to be a monetary value because we're going to be plugging in a number for the t. So let's identify our variables. 22,499 is our initial amount. 11% is our rate. But remember, we have to change it to a decimal, so I'm going to move the decimal point over 2 places, and I'm going to get 0.11. So I'm going to start off with y equals $22,499, parentheses, 1 minus, because remember it's decaying, minus 0.11 raised to the t power. I like to go ahead and simplify what's in the parentheses. And you can use your calculator if you need to. 1 minus 0.11 is going to leave us with 0.89. And that makes sense because it's less than 1. Remember, if it's going to be between 0 and 1, that's a decay function. So there's the first answer that we're looking for. There's our exponential equation. Now we're going to use that exponential equation. And this time we're going to plug a number in for t. And they want us to find out how much is this car going to be worth after 3 years. So we have 22,499 as the initial amount. We have a decay factor of 0.89. We want to find out how much money it's worth after 3 years. Remember that this answer is talking about money. So we want to round it to the hundredths place. That means 2 digits behind the decimal point. So I've got 15,000. Oh, I can't write. $861.10 is how much that car is going to be worth after 3 years. So anytime you buy a brand new car, the minute you drive it off that lot, your car is already depreciating in value. That means it's getting lower. So after only 3 years, it's not worth as much as it was when you first bought it. Obviously, this doesn't include if you buy like one of those cars from the 50s and you renovate it or something like that. Those cars typically are going to increase in value, but with a normal car, definitely depreciates. All right, example 6, we're going to identify the initial amount, the decay factor, and the percent decrease. So according to our equation right here, 200 is the initial amount. The decay factor, remember that's the 1 minus r, that's the thing in parentheses, is 0.71. Then we want to solve for r, so I need to do 1 minus r. I'm going to set it equal to 0.71. I need to subtract the 1 from each side. So I have negative r equals, now you can use your calculator for this if you need to, but 0.71 minus 1 is negative 0.29. I'm going to divide each side by negative 1. So I'm going to end up with a positive 0.29. But remember, we want it as a percent. So I got to move my decimal point over 2 to the right, and I'm going to get a percent decrease of 29%. All right, almost done, y'all. I'm sorry this thing shakes so much. It's just not very sturdy, apparently. Example 7, an adult takes 400 milligrams of ibuprofen. Each hour, the amount of ibuprofen in the person's system decreases by about 29%. So for letter A, we're going to write an exponential equation that models this to find out how much ibuprofen is left in that adult's system after T hours. So let's identify what we know. The initial amount is 400 milligrams, so that's our value for A. It's decreasing by 29%. We got to change it to a decimal, so 0.29 is our value for R. So I have Y equals 400 times 1 minus 0.29 raised to the T power. Now if you want to leave it like that, you're welcome to. I personally like to go ahead and do the subtraction in the parentheses. 1 minus 0.29 is 0.71, so I'm going to leave mine like that. I just like to simplify it. I like the way it looks better. B says how much ibuprofen is left after 6 hours. Well, it says that it is decreasing 29% each hour, so that means that T is 6. So I'm just going to write this on my paper before I use my calculator. Plugging in the 6. And now I need my calculator. So 400 milligrams is the initial amount. Our decay factor is 0.71. We want to find out what's going on after 6 hours. And let's just round it to the nearest tenths place. So I'm going to say that Y is approximately 51.2 milligrams. So after 6 hours, what started off as 400 milligrams has decreased to 51.2 milligrams. Last one, you drink a beverage with 120 milligrams of caffeine. Each hour the caffeine in your system decreases by about 12%. Estimate the amount of caffeine in your system after 7 hours. All right, so initial amount, 120 milligrams. We're going to be subtracting the R because it says it's decreasing. The rate is 12%, but we have to change that to a decimal, so that changes to 0.12. And this happens per hour, and we are doing this for 7 hours. Again, you can plug it in the calculator just like that. You don't have to do the subtraction first if you want. So watch as I do it. I'm going to plug in 1 minus 0.12, and then I'm going to raise it to the 7th power. And again, let's stick with the nearest tenths place. So we're going to say that it is approximately 49.0 milligrams left in that person's body after 7 hours. All right, hopefully you guys think that this is pretty easy. I think these are some of the easier word problems to do that we've done this year. If you're struggling, please shoot me an email, ask me some questions. I would be happy to answer you. We have, sorry, I'm trying to look at my notes real quick. We are going to be going into 8.3 this week, learning a couple of new things. And then next week we do have a quiz coming up. So just kind of keep in mind what we have going on for this week. That will be in Ren Web. And I will see you guys in the next video for 8.3.